Okay, welcome everybody to this week's SPCLB cast. We are very honored to have Viktor Prasanna from USC today to talk about scalable graph machine learning. And without further ado, I'd like Marcin to introduce Viktor.
Thank you, Torsten. Viktor is a professor of computer science at USC. He is the director of the Center for Energy Informatics and leads the FPGA and data science labs. Among other achievements, he was the founding chair of the IEEE Computer Society Technical Committee on Parallel Processing and is the steering chair of the IEEE International Parallel and Distributed Processing Symposium. He is also a fellow of the IEEE, the ACM, and the IIIS. Without further ado, the stage all yours, Viktor. Thank you.
All right. Thank you very much, Marcin. Thank you, Torsten, for inviting me. It's my pleasure to be here. So this talk, I have structured it to be around approximately 45 minutes to give you some high-level view of the problems we face in getting scalable machine learning. There is a particular emphasis towards FPGAs, but it's general techniques. We also use GPUs, CPUs in this context. You can also get more details at my website that I've listed here. My FPGA and dslab websites, as well as my personal website, has these details. Okay, fine. So I'm just going to structure this just to outline here in terms of what I plan to cover today. Just some introduction to graph machine learning, just to make sure what we are trying to solve. Talk a little bit about FPGA technology, just to make sure the talk is self-contained. And the main focus of the talk is looking at some of the acceleration techniques. I look at GNNs, GCNs, temporal graph neural networks. Those are all the kind of the new topic areas we are looking at. And finally, I will have some historical perspectives as well as the directions that we are exploring here in my own research group. So moving along, graph analytics has been an intense area of research over the past several years, almost 7-8 years. The basic idea here is that we would like to use the graph structure to represent, understand, and make some analysis based on the graph structure. Some simple examples, if you go back many years ago, people looked at computing simple properties like centrality, distances, connectivity. These are all the basic properties. So what I'm going to be focused here today is the more recent work in this space, looking at the graph neural networks. There are various versions of it. We will go through some examples of that and challenges and how to accelerate that. There is also a new area of research, what's called streaming graph analytics, where the data is coming as a stream, the graph is changing. I will make some comments about this later on through the later part of this presentation. Also, those of you interested, there is quite a bit of research work as well as commercial work in this space. There are graph databases where you can use graph queries on the data and then discover some properties, make some analysis in that context. So graph neural networks, the basic idea is that given a graph, you want to embed the node features and the graph structure into some low-dimensional vector space. That is a basic idea of what the graph machine learning is doing, what the training is doing for that. Therefore, we represent the graph with all the information that you have along the nodes, along the links into this vector space. And if you can do that, you can solve many other problems, clustering problems, link prediction problems, various node classification problems. All that can be solved efficiently if you can get this compact low-dimensional representation for these graphs. It is very important because we can do many problems very efficiently if you can get this representation as part of the graph neural networks training. And there are a lot of applications of this GCNs, GNNs in commercial systems. I've just given some examples on the right-hand side. There are various vendors, for example, Pinterest, Alibaba, other vendors use recommendation systems based on graph neural network embeddings. Acceleration is very important. These graphs are very large. They can take hours to days to train these kinds of graphs. And also for many real-time applications, you should be able to do the inference very, very quickly in a matter of tens of milliseconds. So in one slide, I've tried to capture here from a computational perspective what these graph neural networks mean and what are the challenges we will face comparing this with, for example, CNNs or DNNs in the space here. On the lower left-hand side, what you see here is the general representation here. It's typically multiple layers like this are stacked to define the graph neural network. You have this input feature vectors here. and then they're aggregated by using this transformation matrix, which is a matrix. There are a number of ways to define that matrix based on the input graph. And then there is do a transformation here. Weight transformation is what is said here. And then you get the output feature vectors here. For each node, you have a vector here that represents that is a representation for that particular vector you have in that lower, hopefully in a lower dimensional space. So this, what I'm showing here is a particular layer of the GNN model. Typically, multiple layers are stacked here. There are various versions of GNNs based on how this stacking is performed, how many layers you have, and how do you define your aggregation function. These define various GNN models in the market today. So I've given the specific details of the various parameters. What is important to notice here, we have a certain number of layers in the GNN model. There is a feature size in each layer. And this is getting transformed by using the adjacency matrix. The adjacency matrix can be defined in different ways based on the various GNN models we have. And then this goes through various transformations layer by layer. And finally, the output layer provides us the particular embedding for those nodes you have. That is the final output you produce here. So our problem here is that given this graph, we want to use this GNN model. There's a particular technique specified in the GNN model and the architecture of the model. And then we want to get embeddings. That is the training problem that we have. That is the purpose of the training. So the model size is something important for us to keep on the back of our mind, because this will come later on for us in terms of what are the challenges. If you look at the GNN model size, for every layer, we have this transformation matrix. That is this particular WL that I talked about here. For layer 0 is what I showed here. And that is a typical size here. Is typically in the range of few hundreds. And typically you store the weights by using 4 bytes per input element we have. And then the total model size is given by the size of this matrices for the various layers. That's what I've shown here. And the model size is not very large, typically in the range of hundreds of kilobytes. Now, when you do the training, typically mini batch GNN training is performed, reduce the memory usage on large graphs. Typically, these ideas evolved. If you go back, the GPU external memory, the GPU global memory is limited. So people came up with various techniques to take a part of the graph, fit that in the GNN and the GPU memory, and then do the sampling. I've also used a couple of keywords here, layer sampling techniques. Like I mentioned earlier, there are a number of different techniques depending on a particular technique that you use what are the nodes that are going to be used as part of the forward propagation in the GNN model. And that's where these various sampling techniques come into picture, layer sampling techniques, subgraph sampling techniques. Those are the various techniques that are used in the community to define what information should be used in propagating the message passing we do in the graph. So to summarize this and put this in a nutshell, what is happening from a computation perspective, from the perspective of today's discussion, not going into the modeling perspective, more from a computational perspective. So we are doing these two operations, which are basic operations you do. You do sparse dense matrix multiplication. That's what I've shown here. This is the aggregation step. And then you do a dense matrix multiplication, which is the transformation step. And these are the basic operations you do in the forward pass in each layer of the GNN computations. And the GNN computations will consist of multiple layers. And also I have defined this matrix here. There are a number of ways of defining this matrix. Sampling techniques define what that particular matrix to be used in your forward pass through the GNN model we have. Just keep in mind this matrix is a sparse matrix. That's where this sparse dense matrix multiplication comes into picture. The weight matrix typically is a dense matrix. That's what is this matrix here. And if you look at these typical sizes here, I've shown here in terms of what is the size of the vectors, encoded vectors you get here as output as you go through the various layers in the system. So before I get into the acceleration technologies, we have just to make sure that the audience is aware of the technologies we will be using. We are using FPGAs. Of course, we also use clusters of devices. We also use GPUs and CPUs, and some of these techniques are applicable in the broader space of clusters of such heterogeneous platforms. So just in a nutshell, just to make sure that we are all on the same page, FPGA technologies, hopefully many of you are already aware of it. Field programmable gate arrays, the basic building block we have is the lookup tables. And then this can be programmed. We also have programmable interconnect. And we can also have a programmable on-chip memory on these devices. These devices have been around for many, many years, almost 30 years now. Essentially, you can compose various functions, interconnect them, and then build more complex structures, and then kind of hopefully you can customize the hardware to the specific application you have, and then program it there. So there's also a large amount of memory bandwidth available on these chips, on these devices, which is very useful for GNN acceleration kinds of problems that where bandwidth becomes very important. What I've shown here is that in the commercial devices in the market today, these are quite sophisticated. There are quite a lot of hardware integration takes in this, high bandwidth memory, static RAMs integrated on this processor IP core, large number of input-output ports, external memory accesses. Also, what is called hard IP in this, we can get various operations, for example, DSP blocks on these devices, which can be used to accelerate the specific integer or floating point operations you do. Just a quick look here about the technologies, what's currently available. This technology is quite advanced at this time. The number of devices are available in the market, which can give extremely high performance. These devices produced by AMD Xilinx as well as Intel devices in the market. Also, I want to just put a quick note here that the technology is even further advancing in terms of building on a single chip, on a single device, single platform, of various units, including DSPs, including FPGAs, including the GPU, what they call the AI accelerators, data parallel machines, plus also ARM CPU cores on a single device with a very large amount of external bandwidth available. So these devices are commercially available now, so you can experiment using this. For example, particularly a device like this is very good for GNN acceleration, simply because we can do sparse computations using the FPGAs and the dense algebra by using the AI engines or the data parallel engines on these devices. Also, just to kind of put a plug here that these devices can also be programmed at high level. Previously, people used to do Verilog or hardware programming languages. But if you go in the market today, a lot of libraries are available, a lot of high-level programming languages are available. That makes it very easy to use these devices. In fact, you can program these devices by using this high-level synthesis in which you can specify your code, which almost looks like your OpenMP code. And then you can also specify inside that what kind of pipelining you want to do, what kind of parallelism that you want to explore, plus interface that with memory controllers, which makes it particularly attractive for graph analytics kinds of problems, where we need custom memory controllers to be able to get high performance in those implementations. I've just shown an example here. What kind of high-level synthesis features exist? I'm showing an example for a classic problem of matrix multiplication. What I'm showing here is that in this example, I've shown here in blue are the various HLS pragmas that you can insert into the code, something that looks very similar to what happens in the OpenMP programming style. The advantage here is that you can use the typical loop optimizations that you do in an OpenMP compiler. Plus, you can also specify some features of the hardware here and let the compiler synthesize the code here. For example, you can specify number of processing elements to use, what kind of pipelining you want to do, and also you can also specify what kind of overlapping of computation and communication you would like to do. And you can also specify how the data layout is performed in the static memories, the on-chip memory of these devices, which can potentially give you very high performance in these implementations. So moving along, what I've done here is that just have given some comparison of these technologies that we are using. On the left-hand side is the FPGA technologies, one from AMD, one from Intel. I've shown also here what is happening in a state-of-the-art multi-core platform and a GPU platform, H100. And also on the right-hand side, I'm showing here one of the largest machine learning accelerators, the Cerebras wafer scale engine. I'm just kind of showing here the opportunities we have for acceleration for the various applications, including GNN training, which is today implemented on all of these platforms. I will go through some examples of the platforms starting all the way from FPGAs. And I'm just showing here the various features here. I'm not going to go through this in detail. What is important to note, if you look at FPGAs, the clock rates are lower. We can do fine-grained parallelism here. We have extremely high on-chip bandwidth that can be used for GNN training purposes. And also that because of this memory controller interfaces can be customized, they can be very, very effective for solving graph analytics kinds of problems. And if you look at the complexity of these devices, they're all in the similar ballpark here in terms of number of transistors that are used here. This wafer scale engine is very large. It is one of the largest, maybe the largest the machine learning accelerator in the market. And these also have excellent peak performance. I've shown here what is a peak performance for various integer representations as well as floating point. So they're all in a very large space of opportunities here for us to be able to look at these devices for training as well as inferencing purposes for a GNN acceleration. So what I will do now is to go into specifics of this acceleration, given these technologies and the basic GNN machine models or machine learning models I talked about here. The focus here for me is to kind of highlight what are the key problems, key issues, and then go through two examples of some recent work we have done here, go through some details of the recent work in terms of one example for looking at the inferencing and one example for training, and then see how we are building these kinds of platforms, more usable platforms, frameworks for GNN training, GNN acceleration. So we are using FPGAs. In fact, we've been using FPGAs for graph analytics for many years. There are a number of challenges here, very large data that is in these graph analytics problems, typically in the range of hundreds of gigabytes, sometimes extending into terabytes of data. So they don't fit in the on-chip resources on these devices. The memory accesses are irregular. There are a number of ways to handle this. I think FPGAs are particularly effective in this context. There's also limited data reuse. In most of these applications, you bring the vector once, the feature vector once, use it, and then you just discard it. And then also, if you look at the complexity in terms of number of operations you do per node, that is quite high in the machine learning on graphs applications. As I mentioned earlier, the memory technologies that can be effectively used for storing these large graphs and also using the on-chip resources, particularly the block RAMs on FPGAs are very useful because you can build multiple of them. You can build multiple pipelines and they can access them as local storage. And sometimes you can also shape them across these pipelines. That gives you very optimized designs for highly optimized designs on FPGAs compared to what happens on GPUs and CPUs. Also, there are a number of new developments. For example, the CXL kind of technologies, shared memory. We can reduce the amount of copying that takes place between the DRAM and the on-chip resources. And also for a lot of the graph analytics problems, fine-grained acceleration is important. We can support them on the FPGAs. And one of the important features that we exploit is the customized memory controllers. We specify the memory controller based on the semantics of the algorithm that kind of hides the memory latencies. We make sure the pipelines are operating at almost close to 100% efficiency in terms of eliminating the pipeline stalls in these applications. And finally, part of our innovation is also in developing new algorithmic techniques, partitioning techniques, computation primitives developed in that context, optimizing the communication primitives, the computation primitives as well, which gives rise to high performance in these implementations. So given a number of references here, we have been working in this space for several years. We have been looking at three aspects of graph neural networks. One is defining these models. Typically, these works are published in machine learning conferences. We are very much interested in acceleration, which is the focus of today's presentation. We're also interested in various applications of graph neural networks. So we have a number of publications of that nature. I encourage you to visit my website and you can look at this. In fact, one of the papers appears at the supercomputing conference next week, where we're looking at the temporal graph neural networks and then see how we can get scalable performance for a particular class of temporal graph neural networks by using GPUs in those implementations. So let me go into the GNN acceleration issues, and specifically what are the challenges, what are the opportunities here, and go through some details of specific acceleration that we have performed using CPUs as well as GPUs. I've shown here there are two important problems, the GNN training problem, the GNN inference problem. For the GNN training, we need high throughput implementations. For every mini batch that you have, we want to make sure that we can complete that. And each mini batch can have a various amount of workload because we're sampling a graph. We don't know how many edges we have in that. So this workload varies for different mini batches as opposed to what happens in the case of a CNN or image-based training that we have. These graphs are very large. The GNN training graphs that we use are very large. I've just given some examples here. And in some of these cases, for it to converge, it can take hours or days for it to converge. On the right-hand side, I'm showing here the inference requirements. We need accurate inferencing, and latency is very, very important. For example, some of these applications, the latency requirements could be in the range of tens of milliseconds. And when we want to do this inferencing here for a typical node that you want to find the embedding, or if you want to do some downstream application on that node, you may be sampling a large number of vertices. And there's quite a lot of research recently about what are important vertices. For example, defining attention mechanisms for graph neural networks. There's quite a lot of machine learning research in this space here itself to understand here how much you should sample. And from our perspective here, even the sampling techniques also add overhead in our scalable performance. So we need to consider that as well, the overall system performance to get scalable implementations. I've shown here the big picture workflow that happens here just from a serially what happens. If you just try to look what's currently happening, if you look at for example, if you see what Amazon DGL is doing, the distributed graph library is doing, the typical steps, you do some graph processing. We may do this once before the epochs, the training starts. Then we do some sampling. Then based on that, you do the feature loading here. This refers to taking those vertex features and putting them into the external DRAM of the GPU or on the FPGA. Then we do these steps I talked about, the sparse matrix multiplication and the dense matrix multiplication steps we have. And then these iterations here, inside iterations here, depending on the number of layers you have here, you perform this innermost loop here, and then you perform this transformation here for that, and then so go get the sampling for the next mini batch, and then you complete the complete epoch here. That's what is the overall steps you perform here. So if you perform this on a parallel architecture, I've shown here what are the steps you perform here. The graph pre-processing you perform once earlier on, and then you can perform this sampling in parallel. That's what I've shown here. Of course, if you have large number of samplers, that also occupies the CPU and the external memory bandwidth, the GPU or the accelerator. And then you perform the basic steps we were performing before. For the serial version, we perform them. And then you have to have the synchronization, all-to-all broadcast typically, to kind of synchronize all the gradients you have. And then you do the weight updates. I've shown the weight updates being locally performed here. I will have more comments to make on this. And then this is the iteration you perform, and then you perform the epochs here and repeat this process. So just a kind of illustration here as to what are the challenges you face in acceleration. I've shown here the execution time for each iteration. I've taken a commercially available software here, PyTorch Geometric here. I looked at on a typical serial processing what happens. I've shown here for various steps for 2 different data sets here, for Reddit and Amazon data sets here. I'm showing here what is the breakdown of the overall execution time in terms of the various steps we do in that, sampling steps you have, the feature aggregation here, including what amount of time is spent in loading those feature vectors, feature transformation, which is a dense matrix multiplication operation, and miscellaneous overheads you have. This is per iteration of a mini batch based training that we do here. So important point here that the key bottleneck here is gathering feature vectors. These are all DRAM accesses come into picture. And then aggregation here is the sparse matrix multiplication you do here to get this implementation. So I'm just comparing here CNNs versus GNNs just to kind of get the perspectives here. In case of GNNs, the model number of parameters is small, maybe in the range of tens of thousands. Whereas in case of GNNs, the model size is very large. For the GNN case, the size of the sample is large compared to the model. Whereas in the case of the GNNs, the model, the image size is small compared to the size of the model we have. And then if you look at the computation and communication, GNN sparse computations, we do computations on small matrices compared to the matrix sizes you have in CNNs. And then When you do the parallel implementations, the model synchronization that you have is typically negligible compared to what happens in the case of GNNs, where the model sizes are very large. This is a very important feature. There are a number of ways we can make use of this information, particularly to exploit the cache memory or the on-chip SRAM on the FPGA devices. So acceleration challenges, in fact, I've touched upon these topics throughout the presentation so far. Large data sizes we have. These real-world graphs do not fit on the on-chip resources on these accelerators. Very little data reuse and memory accesses come into picture. Load imbalance, different mini batches will have different amount of workload. These kernels do sparse, dense, and various kinds of matrix algebra operations, not one type of operation. And then also that there are a number of different graph data sets, different features in these graph data sets, as well as various types of GNN models. There's a number of GNN models. We are interested in supporting as many of those GNN models as possible. So what I will do now is, given this context, to go through two examples here. I'll go through what we have developed here, what is called HPGNN, which is accelerating the training portion here. We are interested in looking at various GNN models and then specifying how we can develop a framework here so that we can take those models and then map them onto CPU plus GPU, CPU plus FPGA platforms. The other result we have, other one that I would like to emphasize today is GraphAgile, which is accelerating inference. It's a domain-specific accelerator we built about the hardware and the compiler. And then I'll go through some details of how we get acceleration in these implementations. So moving along, so the HPGNN, our goal here is to accelerate sampling-based GNN training. There are a number of techniques. As I mentioned earlier, sampling is one of the very widely used techniques to specify what nodes should be used in the message passing. And the sampling is specific for each node. You specify the collection of nodes that should be used here for us to be able to do this message passing inside the GNN model that we have. So our goal here is to look at a CPU and an FPGA platform. The CPU is used for sampling purposes, and the FPGA is used for the basic operations you do in the layer propagations we do. And our interest here is to be able to produce a complete framework in which the CPU and the FPGA will collaborate and then accelerate the overall computations while sharing the external memory bandwidth to the DRAM you have and the shared memory you have in the system. So what we did in this implementation, we looked at the various computation kernels. I've shown here I talked about the dense and the sparse matrix multiplication kernels. On the FPGA, we developed basic systolic algorithms to do this dense algebra. As far as the aggregation kernel is concerned, we use the scatter-gather primitives that is typically used in graph analytics frameworks. And then we use that information in terms of how many of these multiplier units we have available here, and then how many of these pipelines we can build on the device. We do design space exploration so that effectively we can use this bandwidth here by building these multiple pipelines. And if you look inside these pipelines here, they all have the local memory, which is the static RAM on the DRAM, on the static RAM of the FPGA device, what's called as the block RAM in AMD devices. And then we build this scatter piece, and then we do an all-to-all communication here. We build a simple routing network here, and then we do the gather operations here so that when we do the matrix vector, sparse matrix times the dense vector operations, we can combine those results by doing the gather operations. A lot of details here. The systolic array is built. We have a number of buffering here so that we could overlap the DRAM access latencies while this is computed on the systolic arrays for the dense algebra operations. We also have the weight buffer here. Typically, these weights can be stored on these on-chip resources. We have typically hundreds of kilobytes of data. So sometimes we also make copies of this device and then locally store them. So this overhead that is typical in the case of DNN acceleration does not exist in the case of GNNs because the model size, the number of weights you are storing is limited, small, and we can use them. You can save them on using the on-chip resources you have. So these are some experimental results we use the Alveo U250 device, which is one of the state-of-the-art devices from AMD Xilinx. One of the performance metrics here is the number of vertices traversed per second. We want to get scalable performance as we include the number of resources on these devices here. and our FPGA accelerator synthesized at 300 megahertz. And we also have details of the resource utilization. I encourage you to look at our paper. And I've shown here on the right-hand side, lower right-hand side here is what is the resource utilization you have in terms of the various hardware resources you have on the FPGA device for the various graph neural networks models that you have here, GraphSAGE, GCN models that we have here. Now, we also we looked at a variety of GNN models. I've just given some examples here. If you look at the paper, we have a lot more detailed results for various other models as well, looking at neighbor sampling-based techniques, subgraph-based techniques, and the number of GNN models have been proposed over the years. Our interest here in this project to be able to support a large number of such models. So what I'm showing here is a comparison we are making with the baselines. Baseline PyTorch Geometric is a widely used software available in the market. And then the baseline implementations are on CPU AMD platform. And we also have implementations on CPU GPU platforms using NVIDIA A100. These are the baselines that we will compare against. And we'll compare this with our implementations using CPU and FPGA. And quite a bit of large data sets are available. Social network data sets, e-commerce data sets are available. And that's what we use, given some details of the data sets we are using in terms of number of edges, number of nodes you have. Also, what you see here is that what is the feature vector size that we use in the various layers, F0, F1, F2 refer to the various layers in the GNN models. And this shows here the typical number of elements in those vectors that is used here for those implementations. And that's, again, this number of elements per vector can vary, and we do have detailed experiments in the paper to compare the performance. So this is like a one-slide summary of the comparisons here. As I said earlier, we are looking at comparison of throughput, and then we are comparing against CPU only and CPU plus GPU implementations. And I've also shown here what is the average speedup you get here for the various GNN models. That's what is 4 different models you see here. And these are the various data sets I talked about in the previous slide. And then I'm comparing here what happens on CPU, GPU. These are all the commercial available state-of-the-art implementations. And then I'm comparing against what our CPU plus FPGA implementation is doing and what is average speedups you get here. There is also quite a bit of work in the FPGA community itself, looking at accelerating GNNs. There is significant work in the last 2 years, various conferences. You will see those work. There's also work in the context of building ASIC accelerators. This is an example here. And I'm showing here what kind of speedups you can get here by using the FPGA accelerator for these applications in terms of the throughput performance improvement. So let me move on. So this whole research has been focused. It's an ongoing work here in my group to build this complete framework. I call this the general framework here. The goal of this framework is to be able to support a large number of GNN models, and then also to be able to automatically generate the custom code for the FPGA. So the user provides this GNN abstractions on the left-hand side, and then our system here looks at the target platform, and then uses the basic building blocks I talked about, and then it automatically does the design space exploration to compose the hardware, and then it also generates the sampler for us. The sampler runs on the CPU here. We can specify various kinds of sampling techniques depending on the various GNN models you have that produces a complete executable for us on the CPU as well as on the FPGA. So let me move along. I would like to also go into one interesting work recently we have been looking at. There has been, as you know, quite a bit of work at Microsoft and other vendors looking at building broadly applicable GNN accelerators over the last maybe 8 years or 9 years. And then we asked a basic question here: can we build a complete framework, a domain-specific acceleration framework for GNN inference on FPGAs? That's kind of the focus of this work here. So we are looking at the problem of full graph inference. That means the full graph is going to be used in the context of collecting information for the message passing. And then we want to get the node embeddings for those graphs for the inference case. We want to be able to minimize the overall latency here. So what is important for us is to look at this latency of this inferencing. I've shown here, because it is a domain-specific architecture, there is a certain amount of software that comes into picture given the input graph and the GNN model. There is a compilation latency here, and there is also the hardware execution latency here, which is what happens on the FPGA platform. So we will look at this complete end-to-end latency here, which is important in many applications. The model is given, the GNN model is given, the input graph is given. You compile that hardware and the runtime system and compile the code for using the instruction set architecture. And that's kind of the big picture of where the domain-specific acceleration comes into picture. This paper recently appears. I have a reference here if you're interested in more details of what I'm talking about now. So the hardware design here, we defined a complete instruction set architecture, which takes into account the various basic operations you do in the GNN, the aggregation functions, the sparse dense matrix algebra operations, the dense algebra operations. You can also specify the precision that you would like to use in those implementations. So we provide a high-level instruction set architecture here, where you can use task-level parallelism and compile the code. And then at the lower level, we have multiple pipelines. We exploit the data parallelism here. And then the overall microarchitecture supports the various GNNs. That's a goal here, that by using this domain-specific architecture abstraction, that we would like to map various GNNs in the market. There are literally tens, perhaps even hundreds of GNNs in the market today. Our goal is to be able to provide a uniform abstraction and map those various GNN models to a single piece of hardware and configure that using manage that by using the runtime system. So just going into some details of the microarchitecture. Again, we borrowed many ideas from the FPGA work that I talked about earlier, which was focused on inferencing. We kind of optimize the performance by using the multiple on-chip static RAMs available on these devices. And that's where I think some of the performance improvements we get here. And then we implemented this basic 3 kernels that comes into picture in the context of GNNs: sparse dense matrix multiplication, dense matrix multiplication. Also, there is one more operation that we need to perform, what's called sampled dense matrix multiplication. You perform a dense matrix multiplication and then you sample some results out of it to represent what is happening in the nodes or the features of interest for a particular node. So we implemented these 3 operations in FPGAs and made this parameterized, so that based on the different GNN models, you can customize it by using the domain-specific compiler we have. That gives rise to high performance in terms of using this architecture abstraction to compile, to kind of modify the hardware based on the input GNN requirements. So we also have an instruction set architecture, which is the heart of this system here, that not only the hardware microarchitecture and the instruction set architecture we define. The instruction set architecture obviously is the target for our compiler. And this instruction set architecture is kind of a very long instruction word operations, because we have multiple operations happening in parallel. Those operations corresponding to the various pipelines you have in the system. And this particular domain-specific instruction set architecture we defined here to represent how do you perform the various operations. I talked about the dense matrix multiplication, sparse dense matrix multiplication, as well as the sparse, the sampled dense matrix multiplication. So a typical microcode looks like this on the right-hand side. Our compiler spits out this code here, and this is compiled onto this specific instruction set I showed here on this target domain-specific accelerator platform. So going further along, one of the important features of this is this compiler framework, which looks at this GNN models. The user defines this GNN model as input and the input graph here, and it goes through these various steps here. We have a number of optimizations we do here in terms of looking at how do we get the particular architectural features that are exposed to the compiler using the instruction set architecture. And we do a number of optimizations here before we get into the fine-grained task mapping and task scheduling here. This task mapping and task scheduling itself is an interesting problem because the hardware itself is specified based on the particular GNN model we have, the features, the number of layers, the feature vector lengths you have. Based on that, you compose the hardware here and then generate the instruction sequence for the target hardware. So what we did here, One of the important features here is that we developed this intermediate representation, the IR, which is focused on the various GNN models. We looked at various GNN models and then captured here in terms of what are the basic computational steps that are performed here and what is the level of abstraction. We need to go one step beyond what happens layer by layer, and that's what is the details are shown here. So this number of layers is also varying for different GNN models. And then you can specify, as part of the compilation process, it produces this output here, this representation here, which is then used in terms of doing the compilation optimizations. I talked about the 4 compilation steps, and those optimizations actually configure the hardware for you. Configuring the hardware is using various multiplexers, choosing the size of the dense matrix algebra arrays that we want to use, choosing the number of pipelines we want to use, so that we do a small design space. I call it a small design space exploration because this has to happen at compile time, and this is an overhead that we incur as part of this domain-specific exploration compilation that takes place at runtime. So we do a number of compiler optimizations. For example, computation order optimization. So when we do the that aggregation and weight updates, we can exploit the sparsity in that and then do a dynamic mapping at that time. So that's what we do here in this computation order optimization. We can also combine certain layers. Some layers are doing some very simple search operations for local neighborhood that can be combined. Graph partitioning and data tiling, very important for us to be effectively use the pipelines I talked about in the instruction set architecture. Graph partitioning by itself is a challenging problem. There are a number of techniques in the literature looking at should be partitioned along the nodes or should be partitioned along the feature vectors we have. Should we also look at the representations of the intermediate layers? There are a number of techniques. This is a well-studied problem here. Data tiling is something very specific to this architecture, this kind of that has to effectively use the on-chip resources and the number of pipelines we employ as part of the design space exploration. Finally, as I said earlier, we do the mapping of the kernels to the available resources and then do the task scheduling on that. So some experimental results before I conclude the presentation. Again, we're looking at the basic platforms. AMD platform is our baseline. We're using the standard state-of-the-art Alveo platform U250 from AMD Xilinx. And we're looking at various GNN models. We compile them for a number of different models. That's one of the advantages of this domain-specific architecture. And we also run the experiments by using a large number of data sets that's widely available in the literature. What I've shown here is that I've just used this notation here for the various operations, various individual steps that happens inside this GNN models to carefully understand what is happening at each one of those layers and what kind of performance we are getting at those layers. That's kind of getting a little bit deeper into the performance improvement and scalability as we look at the various layers here. And that's what is this kind of the 8 different scenarios that I've defined here based on the various models we have and what we did internally inside those layers. The data sets here, these are all well-known data sets in the community for graph machine learning. I've shown here the number of vertices, number of edges. Also, I'm showing here typical number of features that is used here in those implementations. As I mentioned earlier, our total the performance metric here is the total latency, end-to-end latency here, which consists of the initial latency that you have because of this domain-specific acceleration, the compilation, and we also generate the runtime system, which is doing the mapping and scheduling and managing those resources for us at runtime. This is an innovation of this project in which we actually built a hardware runtime system for this so that we can quickly manage the domain-specific architecture resources for a given input graph and also for a given GNN model. So there are 2 latencies here, latency of the compilation, latency of the hardware execution, and this is a total end-to-end latency in these implementations. I've just summarized here. I encourage you to visit our paper for details. What is the impact of the various compiler optimizations I talked about earlier here in terms of the latency of the execution here? That's what I've shown here. One of the important optimizations is the computation order optimization, significant performance improvements we can get. And again, this performance improvement you get typically depends on the graph neural network model that you are using. That is the range you see here. In some cases, the number of layers is too shallow that you can't really exploit this. In some cases, you will get very high performance. For example, some deep neural network models, GNN models, you can get very high performance in those implementations. So this is a comparison here in looking at cross-platform in terms of comparing against CPU only and CPU, GPU, and comparing with our domain-specific acceleration here. This is the overall performance improvements, speedups you get here compared to the various baselines. And these are all implemented by using some state-of-the-art optimized tools in the market today, PyTorch, Geometric. And I've shown here is the various scenarios I talked about in the previous slide. And I'm showing here in the vertical axis is the speed up. And then I'm also showing the speed up compared to the distributed graph library CPU version and the distributed graph library, the GPU version. These are all the commercial code from Amazon that we are comparing against in this implementation. So in the interest of time, I would like to keep some time for possible interactions and question and answer. So let me spend some time to look at where the area is progressing, what are the challenges as we go forward. Now, there is one important area that the community is engaged at this time, looking at GNN architecture, whatever the model that we are defining, and how do we co-design that in the context of the accelerators we are designing. So it is like a kind of marrying the machine learning community and the architecture or the parallel computing community here. So in the accelerator space, we use this typical metrics that are showing here. We are concerned about the memory bandwidth, available resources, the latency of access. And when we talk to the machine learning model architecture designers, they are concerned about these aspects here. For example, what are the sampling techniques? How expressive is your model? How generalizable is your model? What kind of aggregation functions you want to use? So there is a area of research which is focused on looking at interactions between them. I encourage you to look at this paper here that was published by us in the NeurIPS conference. How do you carefully define this model so that they're effective in using the target hardware? That's kind of the focus of this research. We define new models which are highly accurate, which also have some nice features that are listed here, and also are implementable in hardware. That means they can be parallelized effectively and to get high performance. It's an interesting area looking at the interaction between machine learning and the computing systems or parallelization strategies. There's also another area of research which is very active now, moving from static graphs. In all the examples I've given here, the training and inference is based on the graph structure is fixed. There is also this notion of temporal graphs in which the graph structure is changing. There is a time parameter introduced into it. You may get samples of this time slots. At various time slots, you may have a sampling of the connectivity or the labels at that point, and you want to produce embedding for that. Again, in the interest of time, I'm going to conclude this quickly, but there is our work at the supercomputing conference next week. This work is focused on this large class of memory-based techniques. There are various techniques in this. Memory-based is one important class of these techniques. And we produced a particular scalable platform here, which runs on CPUs and GPUs, what I call distributed TGL here, a temporal graph neural network training framework here. And this works on distributed GPU clusters. And we are able to get extremely high accuracy. When you do this training in a distributed setting, the accuracy drops. We can get very high accuracy here, and then also get a very high scalable training throughput as the number of GPUs is increased in the cluster. So I'm going to stop here. Thank you very much. I would like to spend some time with the audience and see if there are any questions.
Thank you, Viktor. I wanted to take a quick second right now to just advertise the next BCast. We won't have a BCast in 2 weeks because that's Thanksgiving in the US, but in a month, on the 7th of December, we will have Albert Cohen from Google. And now to the Q&A session. If you would like to ask any questions, feel free to either put it in the chat or raise your hand, and then I will either unmute you or read the question from the chat. I think we have Nabil as first person, already 2 messages in the chat, so I'll later read those.
Yes, thank you so much for the nice presentation. On slide 50, you compared against, for instance, libraries such as DGL. And those implementations, you said some of them is CPU only, and some of them, yes, this one. I wonder if this CPU only, is it sampled or mini batch training or full batch training?
So in this case, we are doing full batch training, and then this particular scenarios that you're asking about, what did I do, what kind of sampling that was performed. I provided some details in this slide here, where I talk about what are the various kinds of models that we used and the number of layers that was there, and what particular notation here is the one that I used here later on to. Okay, so these scenarios are all the ones referring to the scenarios in that slide, the previous slide I showed, and these are all the various data sets we used in that context.
Okay, so could you comment quickly in your experience how accurate mini batch training compared to full batch training? I mean, if we have
yes, that's a very good question. I think from scalability point of view, or from a performance or a timing or a acceleration perspective, I think both these techniques are considered by various groups, including us. Now, there is a lot of discussion in the community, the machine learning community. In fact, you can look at the OBGen website. Is mini batch training good, or should we always do full batch training? Right. I think there are examples, there are use cases where mini batch training or sampling approaches have provided good performance, as good as what the full batch training is performed. The full batch training, as you know, is expensive, and also a lot of issues like partitioning and all come into picture. So if you have effective sampling techniques, then the sampling techniques can also provide you high accuracy in those implementations. So there is quite a bit of literature based on the domains where these GNNs are used. And so there is quite a bit of work of that nature that you can look up at in fact, if you look at some of our papers also, we make these comparisons. In particular, our paper that was published at NeurIPS, that looks at what is the trade-off between number of layers you have and then kind of sampling you do, and comparing that with the full batch training approaches. Now, there is also another line of research in the community. I'm sure many of you are familiar with this. Can we bring the notions of attention that is very popular in the transformer community? Can we bring the notion of attention also into the sampling space in terms of what is important to a particular node? Is going to distant nodes important, or are nodes with which are accessible easily in terms of number of hops? Should they be used in that? I think there's quite a bit of, discussion and the models being defined in that context. And the general conclusion here is that it depends on the particular domain. In various domains, these techniques have various accuracy you get in that context. So anyway, I would encourage you to look at my website, as well as this paper, next week's paper I told you about, the one that talks about it. In fact, the paper that is next week is really looking at if you bring dynamic graphs, what is important in sampling? Is the frequency of interactions important? Is the nearness important? Or is there some information in distant nodes that we should capture? And how do we capture that? So it's interesting questions. I encourage you to look at that paper as well.
Yes, thank you. Thank you so much.
Maciej?
Hello. So I have a question regarding how do you approach GNNs in general in this in your framework mathematically? Because when speaking about GNNs, you can see, for example, a single GNN layer through either so-called localized operations you just run on each vertex, in the so-called local view, where you basically say, okay, for every vertex, I will basically run the layers from the perspective of the vertex, right? So you run the iterations of the vertex, you cover its neighbors, embeddings, you do some local computation, and then you update the embeddings, and you go on, or you view it for the perspective of linear algebra operations, where you see all the embeddings together in a matrix, and then you just do matrix products. And I just wonder which of these two approaches are you using in your scheme?
Right. So I think it's a good point in terms of how do you look at these operations? Do you look at it as a localized operation, or you look at it a global operation of a large matrix of matrix operations?
Yep.
So all these approaches are looking at it from a localized partition of the matrix is used. And this particular approach is effective in the sense that many of the sampling techniques look at it, take a localized view from each node, and then they try to gather the information. So our approach here is based on looking at this localized from the node perspective, or what I call here, we generalize the node perspective in our paper that was published in ICLR 2021, in which we said that let's look at it more from a subgraph perspective as opposed to a node level perspective. The problem with the node level perspective is that, yeah, it gives a nice localized view, but there are some redundant computations that you don't make use of it. So
Yep.
From a computation perspective, if you can effectively define a notion of a subgraph and then propagate inside the subgraph, there is also scope for improving the accuracy as well as improving the acceleration performance, simply because there is effective data reuse in that context. So that is the idea that we proposed in terms of model depth and the scope of what we call as the target region for a vertex or a collection of vertices. So I think we took the subgraph approach, which is kind of in between a node perspective and a full graph perspective. And that subgraph perspective gives nice optimizations, and that's something that is explored in our work. And then if you look at our papers, we go into those details.
But then what do you exactly mean with subgraph perspective? Because in the matrix perspective, in the kind of global perspective, you basically have the adjacency matrix and then the embedding matrix, right? For your current embedding state, and then you just do the multiplication. But then in a subgraph perspective, what do you exactly mean? I mean, do you have embeddings per subgraphs and somehow?
Right. So you do the embeddings in the subgraph, and then you propagate across the mini batches to the global graph that you have.
I see. Okay, so you basically play more of the game of the higher order here. Somehow you try to hierarchize the graph and okay, I see.
Right. So I think that I think the whole issue of given a large graph, there is information in the large graph, and then you're looking at a local view or a subgraph view, and then how do you kind of propagate from the local view to the global view, right? And that's where these attention mechanisms, graph sampling techniques, they all come into picture. And then how do you go across them? Maybe the number of epochs comes into picture in your training convergence, and that kind of propagates across the entire graph. Again, this idea of local versus global or subgraph versus a complete graph, there is quite a bit of research in terms of the accuracy you get, the training time, and that's something I would encourage you to look into.
Yep. I mean, there's one benefit if you use the kind of the algebraic view, right? It's basically you can throw in the communication avoidance machinery that you have and just get the performance benefits basically for free. I mean, hopefully.
Right. I think as long as you can, yes, as long as you can handle both sparse and dense operations in a unified way.
Of course. Yeah, of course. I have one more crazy question. So there are some very early papers claiming that basically generative AI LLMs will replace GNNs, and you have preliminary papers like GraphText that basically say, okay, we push the graph into the context, and then we just try to basically see if we can get some predictions based on what the underlying model will tell us in the basically inference pass. And I was wondering, what do you think about these things and these works? Because you do have also quite some resonance in the graph community with designs that, for example, focus on in context basically graph representation and coding and in context learning for graphs. And I was just wondering if you are also looking at that direction.
So we're not looking at that direction, but we are looking at some cross between GNNs and the generative AI models. There is some preliminary work we have in that context where we can use this temporal space here to bring additional, essentially we want to look at more dynamic versions as opposed to static versions. If you look at this generative AI models, there is a dynamicness in that particular kind of inferencing that you do, which is not there in the static. You'll use the static GNN models, whatever I talked about today, most of it, except for the last two slides, everything is statically kind of learned from. So we are looking at this, how do we kind of, in the generative context, can we mix GNNs in that context? I don't have specific results at this time, but the question you're asking is a very interesting question. But again, I don't believe that this generative space will take it override something. And that I think there is
Yeah,
some
I don't think so.
opportunity here to combine these two. That's what I feel.
Yeah. I mean, not for the big graphs, right? This is clear, at least for now. But yeah, it's an interesting thing. Okay, thanks a lot. I will now hand over to other people.
All right. So thank you very much. And Marcin, Torsten, I'm going to have to leave here for another meeting at 10. I'm always available. If there is anyone wants to send me email, I think my last slide has my contact information. I encourage you to contact me. Very good questions. I appreciate these questions. I think it's somewhere here. Yeah. Okay. So please contact me if you have any questions. I apologize. I need to leave now. Thank you.
Thank you. Thank you, Viktor. Have a great day.
Thanks, everyone. Yeah. Bye-bye now. Thank you.
Bye-bye.